So we are going to be finding the area between two curves. When I teach this, you're probably just going to be like, haven't we learned this before? Because you kind of have. The only difference is like kind of two things. So far, we've only done the area between a curve and the x-axis. Now we're going to put a second curve in there. It's really not very much different. And the other thing is you can have a sideways problem and it would be dy instead of dx, where the whole thing is just backwards. The easiest way for me to explain it is by doing a problem. But the way it's going to work is, when I say rectangles, do you remember the Riemann sums we did where you had all those rectangles, you add them up? If you have vertical rectangles, like you're adding up all your areas this way, that's a right side up problem. It'll be dx. You're going to do the upper curve minus the lower curve. This is actually what we've been doing all along. It's just when the lower curve was the x-axis, that's 0. So we did the upper curve minus nothing. So we just didn't put it in there. But you've been doing this all along. It's just now you actually have something that's going to get written. Now, if the problem is sideways, all your rectangles are sideways. So it's going to be the right curve minus the left curve, and it'll be a dy problem. And you have to make a full commitment to the whole thing being sideways. Here's the only thing that gets people. How do I know whether it's dx or dy? This is a totally crap answer, but you kind of just have to look at it and see if it's right side up or if it's sideways. I don't have a good answer for that. There's not like a definite way to tell. Like, is this graph over top of this one or are they next to each other? It's going to just come with practice. Okay, so you're going to have to just trust the process. So let's go ahead and look at the first one. We're going to find the area bounded by all of these graphs, which means you have to have some graphing skills. So like thoughts back to algebra 2 and pre-calc. This is going to be a parabola moved up 2. So we're going to start at 0, 2, and you're going to have to be really particular about your points because you need to find the intersections exactly. So you can't just be like, oh, good enough, like it has to be right. All right, and then what's another point that I can put on that graph? So we started 1, 3, good. And so also -1, 3. And then let's do 2 more. What is another point we can put on there? Good, perfect. -2, 6. And then 2, 6, good. It's like a buy one, get one deal. So here's your parabola that's moved up 2. Okay, so let's plug in 0. If you plug in 0, you are gonna get 3. So 0, 3. We're gonna plug in some other small numbers. Let's plug in 1. If you plug in 1, you're gonna get 1 minus 3, that'd be -2. Minus 1 would be -3 plus 3, 0. All right, now let's plug in 2. I'm gonna have to write this one down because at that point I can't do it in my head anymore. 2 cubed, 8. 2 squared is 4 times 3 is 12, so -12 minus 2 plus 3. All right, so if we plug in 2, what are we gonna get? That's all gonna add and subtract to be, is that -3? -3? So 2, -3. And then let's plug in 3. 3 cubed. 27, good. 3 squared is 9 times 3, 27, which is convenient, right? -3 plus 3 will be 0. And now we need to do the other side. So let's do -1. If you plug in -1, that's going to be -1 minus 3 would be -4 plus 1, because negatives cancel. So that'd be -3 plus 3 is 0. So here is your graph. I know you're like, why'd she make us do that? I don't know. I think it's just good for you to have to plug in some numbers and get through the math sometimes because you're gonna have to be able to do it. So the way I know, that's a good question. The way I know I'm done is this is an x cubed. So I know it's gonna have 2 bends in it. So once I found both of them, I know I've like, these are gonna just keep on going. All right, the x-axis, and then the vertical lines, x equals -1 and x equals 2. So this is the area that we're finding. Now, I know we've talked a lot about accumulation and how we have like above sea level and below sea level. That kind of goes out the window for this unit. When it says find the area, you just want the total area of that space. It all counts positively. Do you understand what I'm saying? Like it's just the area of that. So we would want to integrate from -1 to 2, and we would need to absolute value the equation. Why? We want it all to be positive. So it'll be absolute value of this x cubed minus 3x squared minus x plus 3 dx. You can go ahead and put that in your calculator because I can't make you antiderivative and absolute value. That is not a thing, right? Yeah, and again, remember the absolute value ones kind of take a second sometimes. Don't hit any other buttons, just wait. The calculator's just like, quote unquote, thinking. And you should get 5.750. We also typically don't do units for these. They just generally don't give you any. But like, say it was inches. We found an area, so it would be inches squared because it's an area. Again, they just generally don't give them to you. Did typing that? No. Okay, find the area bounded by. Oh, that's a little weird. This one's going to be a sideways problem. I know I said that there's not really a definitive way to tell, but this is like a huge clue. The equation's written backwards. Instead of y equals, it's x equals. You see what I'm saying? Okay. So a lot of times it helps people to make a chart of values. If you can do it in your head, that's totally cool, but I'm just going to show you how to do a chart of values. Instead of plugging in for x and getting y, you're going to plug in for y and get x. So it's backwards, all right? I would still start with 0, but notice how I put it under the y column. So if you plug in 0 for y, what are you going to get for x? 3. Good. Now we're going to plug in 1. I'm actually going to do plus and minus 1 for y. How come it won't make a difference whether the 1 is positive? Because it's squared. So I would just knock them both out at once. Plus and minus 1. If you plug in 1 or -1, what do you get? 2. And then I would do plus and minus 2. Again, plus and minus, because there's a squared, it's not going to make a difference. So if you plug in 2, 2 squared is 4, 3 minus 4, -1. Go ahead and plot those. It will not be a function. It's going to fail the vertical line test. It's going to be a sideways parabola. That's fine for these problems, though, because we're just trying to find an area. It's just an area of a shape. So they won't always be functions. We're going to do the entire thing sideways. Like it's going to be a dy problem where the whole thing is going to be reversed. I think I'll be able to answer that question better once we start setting up the integral. So can you hold on to it? Because I think I may end up answering your question once we get there, but you'll have to stick with me for a second. And you would get a plus and minus square root. Yeah. Is this stuff, I know you saw this last year, but isn't this the stuff that you didn't see as much because it was towards the end and this at all? You might not have. Okay, cool. I'm teaching you something new. That's awesome. All right. Y equals x minus 1. So that's going to start at -1. So right here. And then the slope is 1. So up 1 over 1. Oops. I pointed to -2 instead of -1. So this is the area that we're finding. So again, this is a thing where I can't like force you to see it, but do you see how there's not a clear-cut upper graph and lower graph? Like I don't have one graph above the other for the whole time. So it's gonna be right graph minus left graph. I know people know their right from their left, but if every year somebody's like, I just can't tell which one's which. And I told them to put an R and an L and suddenly like it like worked. I don't know why, but if that helps you, put that on there. This is the right graph, and then this is the left graph. You have to make a full commitment to the whole thing being sideways. So you need both the equations to be x equals. This one already is x equals. What would you do to this one to make it be x equals? Yeah, add over the 1. So do you see the two things I circled? Those are what you're going to use. Also, when you set up the integral, you have to use y values. The entire business is dy now. So look at your intersections, and sometimes it helps if you bold them. You want the y values. You're going to integrate from here to here. So what are your y values for those? Yeah, -2 to 1. Do you guys see what I'm saying there? Like, a lot of this is like, I have to just point to it and be like, hey, do you see it? It's from here to here. We're going to do right graph minus left graph. The right graph is the parabola. That's the 3 minus y squared minus the line, which is the y plus 1. dy. Don't write dx at the end. These are y values. All of this says y, and then that has to say dy. If you start mixing and matching, I have to take off points for that, and you're going to be bummed. So just don't do that, right? So let's clean that up before we do the antiderivative. This would be -y squared minus y, and then we would have 3 minus 1, so plus 2. And so that would be -1/3 y cubed minus 1/2 y squared plus 2y. Almost everyone puts 2x, and then I have to take off points, so just be careful with that. Such that -2 to 1, upper boundary minus lower boundary. So if you plug in 1, it is -1/3 minus 1/2 plus 2. And then if you plug in -2, it will be 8/3 minus 2 minus 4. If you were to work that out, it would come out to the exact same answer as this one, because if you notice, it's the same shape, just sideways. I did that so you could do a compare and contrast. All right, find the area bounded by. Ooh, do you see how these are both x equals? It's a big clue that it's going to be a sideways problem. X equals y squared is going to be a regular old parabola, just sideways. So you can make a chart if you want for that one, but I think it's easy enough because it didn't get changed at all. You'll have 0, 0, 1, 1, 4, 2. What would the next point be? Only it would be 9, 3, yeah. But you could turn your paper and just do 3. Oh, did you turn your paper sideways? 16, 4, yeah. Anyway, it's just a regular old parabola, just sideways. Yeah, I'm gonna give you a graph that it fits on. They're not. So like that, you get kind of a clue from me, but. All right, and then this one, I'm only gonna make a chart for like a couple of points, and this is gonna be linear. So like the slope instinct should kick in at a certain point, you can just keep it going. If you plug in 0 for y, and I just always start with 0, what would you get for x? Be 4, right? And if you plug in 1 for y, you would get 7 for x. And that's honestly good enough. You can just take those 2 points and continue the slope for them. So we'll have 4, 0, 7, 1. And so the next one would be 10, 2. Like, do you see how it's over 3, up 1? Like, yeah, it's gonna be linear. So just allow the slope instinct to kick in. So we're gonna find the area of that shape. Looks like a whale to me, like a whale tail or something. Like, I don't know. That's what I always see when I look at it. Like that's its tail. I don't know. of the statue. All right, you need y values. So it'll be from where to where. Look at your y-axis. Good, -1 to 4. We're going to do right graph minus left graph. If writing those in helps you, then do it. The right graph is the line, so that's going to be the 3y plus 4, minus the parabola, which is the y squared, dy, and then antiderivative. This would be 3/2 y squared plus 4y minus 1/3 y cubed, such that -1 to 4, upper boundary minus lower boundary. So let's see, 4 squared, 16, divided by 2 is 8, times 3 is 24. So that'll be 24 plus 16 minus, 4 cubed. Do you guys remember that one? All right, 64 thirds, good. And then -1, that's going to give you 3/2 minus 4 plus 1/3. You're doing good on time. We'll do one more and then we'll do a brain break. So number 6 says, find the area between that graph and the x-axis for numbers bigger than 1. So that means we want our integral to go from 1 to infinity. Okay, so this is an improper integral like what I taught you last unit. So it'll be from 1 to infinity of this e to the -3x dx. Hey, Ms. Cole, why didn't we do upper graph minus lower graph like all the other ones? Because it said between that graph and the x-axis, which would just be 0. You could write -0 if you want, but it's not necessary, right? So this will be limit as b goes to infinity, integral from 1 to b. Oh, there was one of these on last year's exam. You know how we just did question 1 from last year's exam? Like I worked out the rest of them though. There was one like this and you got a point for setting it up with the limit. All right, e to the -3x dx. We need a u substitution. What would we let u equal? Yeah, -3x, good. The derivative is -3. We're going to adjust with a -1/3. All right, so it'll be limit as b goes to infinity. -1/3 goes out front, du goes at the end. What's still there is e to the u. I'm gonna have to come over here, I ran out of space. E to the u is its own antiderivative. So it'll be -1/3 e to the -3x such that 1 to b. I don't know why I started writing all that out, because did we really need to do all that work? Actually, in hindsight, if there's a -3, just slap a -1/3 out front. It didn't hurt us anyway. All right, so don't skip this step. Upper boundary minus lower boundary. So it would be -1/3. Now, since that's a negative exponent, I'm going to bring it back down to the denominator. It would be -1 over 3e to the power 3b. Minus, and then this would be -1 over 3e to the 3rd. Because if you plug in 1 times 3 would just be 3. All right, and then lastly, you're going to evaluate the limit. So as b goes to infinity, what does this first part go to? 0. The denominator gets huge. The whole thing's going to go to 0. Negatives cancel, so plus 1 over 3e cubed. And so that would just be your answer. Okay, so to find the arc length on a graph, I'm just going to give you this formula and we're going to practice a couple of problems with it. They use S for arc length, which I'm really not sure why, but that's not important. It just, you have to memorize the formula, right? So there you go. S for Sean. So it's integral from, and they're going to give you like the starting point and the ending point, and then it's this great big square root, and it is 1 plus the derivative squared dx. So there's one more thing for you to memorize. All right, I know. Big old square root 1 plus the derivative squared dx. I'm going to show you what it is you're actually finding though, because I don't want you to just memorize that and get an answer. I mean, I do, but I also want you to get what's actually happening. So here's your function, e to the x plus 2. I'm just going to sketch that really quick off to the side. E to the x is a swoop. It just got moved up 2. So you're going to have your horizontal asymptote at 2, and it's going to do something like that. Are we all visualizing this graph? Okay. So here's -2, here's +2. When you're finding the arc length, you're finding a different color here. Not that it'll show up real great on here though, but you're finding this distance, which again is kind of neat, right? Because you're finding the distance of not a straight line, but like a curve. Like you're finding that actual distance. That's cool. I can disagree, but I'm right. So that's what you're actually finding anyway, for what it's worth. All right, so this will be integral from -2 to 2. And then my suggestion is set it up first. Just draw yourself a big old square root, 1 plus blank squared. Just do that, do 1 plus blank squared, and then you can fill in the derivative. I gave you an easy one to start with, because what's the derivative of that function? Yeah, e to the x. And also, I'm going to allow you to just type this one in your calculator. So everyone go ahead and type that. But don't be like, oh, I'm not going to type it. Typing it is a skill that you need to practice, because if you hit one button wrong, it's not going to work. And so you do need to practice that. So everybody just go. All right, so 9.010. Again, they don't typically give units for these, but if there were, it would just be feet or centimeters or inches or nanometers or whatever it is. It's just a length. All right, so let's try and set up this one. It will be integral from 0.5 to 2. And again, just set it up. Draw yourself a big old square root, 1 plus blank squared. And then you can put the derivative inside of them. I know myself, you know yourself best. I would forget the squared if I didn't do that, to be perfectly honest with you. Because by the time I was done figuring out the derivative, I would just forget to put the squared. So like set it up with a blank. And now we have to go back and do the derivative of this. All right, derivative of x cubed, 3x squared. Now this one gets a little weird. This is 1/2 x to the -1. So that derivative would be -1/2 x to the -2. And so that brings the x back down to the denominator. So it would be -1/2x squared. That one was tricky with the negative signs. All right, go ahead and type it in. Be really careful with the parentheses. You definitely need the parentheses on this one. And do you guys all know how to do the alpha y equals and get the fraction bar? Okay, because that helps a lot too. Because that does save you from having to use parentheses sometimes, and it makes it like look a little bit nicer. What's that? Oh, it has to think on this one a little bit. Isn't that like, that's like a pat on the back. Like you've gotten to such advanced mathematics that your calculator like can't even figure it out right away. Like, anyway, did you get 7.613? Okay. And then I have 2 on here where we are going to actually work it out by hand, because sometimes you might have to do that, right? That's why there's a whole lot more space for these. So this would be integral from 0 to pi over 4. And for extra fun, this one's going to involve the unit circle, which is my favorite. Gigantic square root. And it will be 1 plus blank squared. So it's like ln got hungry and ate cosine of x. What rule is that? Chain rule, okay? So derivative of the outside, derivative of ln would be, well, it'd be 1 over x, but it's 1 over like whatever's there. Good. So cosine goes in the denominator. And then you chain on, so it's going to go in the numerator, the derivative of cosine, negative sine. Now, it's not going to matter so much that it's negative because we're going to square that. And when you square something, it'll just be positive all the time anyway. So this is going to be 1 plus sine squared over cosine squared. And we have a little bit more simplification to do. Again, I left room because there's going to be a little bit of writing for this one. How would we simplify sine squared over cosine squared? What's sine over cosine? Tangent, it would just be squared. Yeah, good. So that's going to simplify to be tangent squared. And then I kind of don't really expect anyone to remember this identity, especially because pre-calc like knocked you guys out at the end of the year. And it's also like kind of a real random one. But 1 plus tangent squared is secant squared. And the reason that that helps us so much in this problem is if you have the square root of secant squared, what's going to happen? It's just going to be secant. Yeah, the squared and the square root cancel out. Unfortunately, then you have to have memorized the antiderivative of secant. Who is secant's buddy? Which trig function does secant go with? Tangent. It is ln secant plus tangent. I'm throwing like every identity possible in memorization into this problem. Not me, I mean, that's just the way the problem turned out. But anyway, and now we're going to do upper boundary minus lower boundary. And here's where the unit circle comes in. There's like so much review in this one problem, it's great. Pi over 4, if you don't want to draw it, fine, okay, but you do need to know how to get through the problem. What are the sides of the triangle for pi over 4? Perfect, square root of 2 over 2. I always write it because that only takes a second and then I can visually see it, all right? Oh, I forgot my LNs. Oh, where's my LN needs to be in there. I'm sorry. So 1 plus tangent squared equals secant squared. That's just a trig identity that's like, it's just true. I don't have like a real good explanation for that one. It kind of just is. It's kind of like sine over cosine equals tangent. 1 plus tangent squared is secant squared. It is.